Good morning, good afternoon, good evening, everybody, depending on where in the world you're joining us. I'm Jarka Glassey. I'm the Vice President Executive of the European Federation of Chemical Engineering, EFCE, and this is my second term as Vice President. I'm actually a biochemical engineer by training, and I graduated from the Slovak Technical University in Bratislava, but I work at the Newcastle University in the UK, basically all of my life as a professional chemical engineer. And I'm really happy to be involved in the introduction of this webinar on high pressure technologies for sustainable energy sector. And I'm really looking forward to participating in the webinar for at least a little while that I can. Let me just say a few words about the Spotlight Talk series. So this is now our 5th year of the Spotlight Talk initiative, which started in 2020 to help us keep together the community during COVID pandemic. And the success of the previous years convinced us to transform the Spotlight Talks into a regular feature of EFCE program. And now we have one Spotlight Talk series in odd years and 2 in even years, like 2024. And this autumn, 13 of our working parties and sections are delivering over 2 weeks short sessions of 3 to 4 talks focused on specific topics by leading industrial and academic experts. And the series therefore enables attendees to sample matters in new areas and encourages cross-fertilization of interest. If you're interested in the full program of this Spotlight series, please visit our EFCE website. And since I mentioned EFCE, if you're not familiar with it, EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, representing more than 100,000 chemical engineers in Europe. The working parties and the sections that EFCE has cover all major specific aspects of chemical engineering and are in fact at the core of our organization, forming the scientific engine that drives many EFCE activities. They provide an important forum for technical exchange and networking amongst chemical engineers in Europe. I'm particularly happy that in this series of Spotlight Talks, we have the first contribution of the newly re-established section on sustainability, with one separate Spotlight Talk series that happened earlier this week, and another one co-organized with the Working Party on Education, which will take place next week. So before concluding, I would like to thank all the people who worked hard within the working parties, sections and EFCE itself for this initiative to happen and to be successful. In particularly, many thanks again to our EFCE's Martin Poot in Toulouse, who did most of the conceptual setting up and practical activities. Thank you, Martin. And thank you for your attention, and I wish all the speakers and the attendees a fruitful and successful webinar. And now I will hand back over to my colleague, Edith Székely, who will take us through the webinar, and she will introduce a bit more about the webinar and handle all the rest of the facilitation. Thank you, Edith.
Thank you very much, Jarka. I hope that you can see my screen now. Could you please confirm? Yeah, is it okay?
Yes, yes, it is.
Okay, thank you, Jarka. So this event is organized, this session is organized by the High Pressure Technology Working Party of the EFCE. And in this slide, I just showed you the site, that in the site of the web page within the EFCE, this is efce.info. If you are interested in the work of the working party, just contact, please, the chair, Professor Koseru, or the secretary, Professor Gemze. Actually, besides meetings and conferences in the high pressure technology field, the major activity of I'm sorry, I just cannot switch my slide. Yes, the major activity of the working party is the organizing of the summer schools. This is a traditional one organized by Professor Gamze, but the members of the working party participate as lecturers during this 2-week-long event. And this covers from the fundamentals to the applications and industrialization, a wide range of knowledge within this field, but also serves to build a community. And over the decades of this annual organization of the course, more than 1,000 young career chemical engineers or early career chemical engineers and chemists participated in this course. And we are still running it and wish to run it longer. And in this slide, you can see the date and the time of the 2025 event. And please, if you are interested, just write directly to Professor Gamze. His email is just on the slide. Or if you cannot do that, then you can contact anyone within the high pressure working party, because we can just switch the word and let you know all this information. For coming back to the spotlight talks, this is already the third session organized by the working party. The first was organized by Maria Jose Cosero, who is the chair of the working party. The second one by Irena Zizovic, who is one of the members and working on the Wrocław University. And you can find the recordings of these events online as well. So I'm encouraging you to check. Today, we brought you a session highlighting 3 compelling examples from large-scale industrial advances to innovative engineering and research areas to serve the green transition of Europe. And we here hope that this session will help you to discover how pressurized fluids are pivotal in enhancing heat utilization and boosting energy efficiency. And then we will delve into the critical process of carbon capture and storage technology, which captures and stores carbon dioxide generated during energy production or other industrial activities, preventing it from entering to the atmosphere. And I mean that this is supercritical, so high pressure technology. And also participants will learn about current CCS projects and operational and nearing completion. And while at the end of the session, we may gain new ideas and emerging techniques and aim at repurposing carbon dioxide as a valuable carbon source of the future. Because if we want to do a circular economy, it's very important that the CO2 we are producing anyway is not just stored, but also used in our industry. Before passing the word for our first presenter, I would encourage you to write your questions in the Q&A part of the Zoom. And during the presentations and during the whole session, please be muted. And these questions you write in the Q&A, and please do it, will be read out for the presenters and they can answer it at the end of their presentations. And also, if some questions are left, we can discuss it at the closing of the event after all the presentation, and you can still get answers if something remained unanswered. So I think it's high time that I give the word to Professor Imre from Budapest University of Technology, if I'm able to stop sharing my slide. So the word is yours.
Thank you very much. And thank you for this opportunity to have this talk here. I hope all of you can see now my sharing. Yeah, can you see it?
Yes.
Okay, some of you might remember me because although originally I'm a physicist, but in the late 90s and the early of this century, I was more active in the field of high pressure phase equilibria, high pressure miscibility. I spent a few years with Professor Bernhard Wolf in Mainz and with Ulrich Deiters in Köln. But then my life changed. I moved in a different direction and started to work on energy production. And recently I am working in a technical university in an engineering department. And today I am going to talk about the utilization of heat with the help of supercritical fluids to generate power. And okay, so let's start it. All of us know that more and more electricity is produced by renewables, by solar, by water, or by wind, but still most electricity produced all over the world are produced in big power plants. And in big power plants, they are making heat on some way, for example, in nuclear power plants by nuclear power, or in fossil power plants, they are just burning coal or oil or whatever. And then this heat will be turned to work, and from the work we can generate electricity. There are other smaller units when we are using pre-existing heat, for example, geothermal or solar heat, and we are utilizing this heat to generate electricity, but more or less the method is similar, just the materials and the numbers are different. So how can we produce power from heat? Usually I'm saying to my students that we are very lucky, because from the 4 laws of thermodynamics, we need only 2. According to the first law, we can play with work and heat, because only the internal energy has to be constant in a closed thermodynamic cycle. So we can turn heat to work or work to heat, depending on what we have and what we want. But the bad boy, the second law, is saying that life is not ideal, so not all the heat can be turned to work. Therefore, we have to figure out how to turn more and more heat to power. And if we can do it, we can make some electricity, which is very good. When we are using thermodynamic cycles, the best way to do it by using temperature-specific entropy diagrams, because it's very easy way to calculate the heat in this way. And in this figure, you can see the traditional Carnot cycle. Carnot cycles has 4 steps. It's a gas cycle. First, we do have a compression cycle. During the compression, the gas temperature will increase. If it's fast enough, then we can do it adiabatically, so the entropy is more or less constant. Then we are reaching a high temperature, high pressure state when we are adding heat to the system. But for some reason, Carnot decided that it should be done by isothermal way, so heat addition without temperature change. After adding sufficient amount of heat, we can turn some part of this heat to work using an expansion device. The expansion device will expand the hot, high pressure gas, and we will have cold, low pressure gas, but there will be some remaining heat in the system, which has to be removed. So therefore, this unused heat has to be removed from the system by a cooler. And we can easily calculate what is the ratio of the heat which was pumped into the system turned to work. And in this case, because simply we have to compare the area of the double-shaded and the total rectangles, it will turn out that the efficiency is 1 minus T minimal, which is this medium. I hope, can you see my mouse, my cursor?
Well, hardly, so. But we can.
Yes,
okay.
A little bit.
Okay, thank you. So this is the T minimal of the cycle, and the upper one is the T maximal. So simply we have to divide it. Obviously, we have to do it with Kelvin, which is quite bad, because it means that T minimal will be always around 300, because in industry we have to use air cooling or freshwater cooling, and it's around 300. So even if T max is quite good, we cannot get very nice numbers. But it also showed us that the best way, the highest efficiency would be to use some thermodynamic cycle, which is graphically resembles to a rectangle. So it's very easy because even if you draw some crazy thermodynamic cycle, you can easily see whether it's rectangular or not rectangular. Carnot cycle would be perfect, but the problem is that in a gas cycle, to solve the isothermal heat addition is quite difficult. Let's say it's more or less impossible. Therefore, we have to figure out something. Let's keep the working fluid, the gas. What can you do with a gas? Of course, you can do adiabatic compression and adiabatic expansion, but the most simple way for heating or cooling would be an isobaric way. So therefore, the easiest gas cycle would look like this one. First, adiabatic compression, then an isobaric heating, then an adiabatic expansion, then the isobaric cooling. This is a so-called Joule-Brayton cycle, specifically the closed one, which is using external heating. If we put this Carnot rectangle around it, we will see that the rectangle is much bigger. The area within the Joule-Brayton cycle is no more than 30% of the total rectangle area. It means that we are not utilizing all the heat what we could do. And well, we should do something. We have to figure out how to make isothermal heating. And of course, you can make isothermal heating if you just let the gas and you can try to use some phase transition in your system. So you have to use some liquid working fluid, which is liquid in low temperature, heat it up to get steam or vapor. And with the phase transition, you can get isothermal heating parts and isothermal cooling parts. This is the so-called Rankine cycles. The traditional power plants are using the steam Rankine. There's also some carbon dioxide Rankine and the organic Rankine cycles, which are using various organic fluids. There is an additional problem. It is especially serious when you are using the so-called pre-existing heat sources, which is waste heat or geothermal heat or whatever, because in a nuclear power plant, you have plenty of heat. But in a geothermal well, you have only a small amount of heat, which means that from small amount of heat, you can generate only small power, small profit. Small profit means that you have to make your investment on a very low level. It means that your device, which will realize the thermodynamic cycle, has to be as simple as possible. And let's see, this is a carbon dioxide TS diagram. Let's make it schematic because it's not important that it is carbon dioxide. So in the TS diagram, you have the liquid part in the low entropy side, the vapor part on the high entropy side. Below the bell curve, you have the mixed liquid and vapor region. And of course, somewhere up, you have this high pressure supercritical region. And let's try to make ideal cycles in the first step. This is the so-called carbon dioxide or organic Rankine cycle, the red line. You can see that it is a little bit like a rectangle, but some part is still missing. First, we are starting with saturated liquid state, and we are compressing the liquid with a pump. It's a very short arrow because in temperature diagram, even high compression means only small temperature change because we are working with liquid. Then when we have the pressurized liquid, we can start to heat it, and upon heating, the liquid will go closer and closer to the saturated state, and then it's going to reach it, and after reaching, the evaporation will start. This heating has to be done by two different heat exchangers because the liquid heater has two liquids, which means that high density, high viscosity fluids, while the evaporator has also vapor inside, which means that it's a low density, much lower viscosity fluid. So the two separate heat exchanger will be needed. Of course, we also need a heat source, the red one, and the cold source, the blue one. So when we have the evaporated high pressure liquid, it's not liquid, it's already vapor, then we can expand the vapor in a so-called expander, and then it will go down. If the expansion is ideal, then it will be adiabatic, so it will be a straight line coming down, and the expander will be connected with the generator. Generator will make the electricity. At the end of the expansion, we are below these bell curves, close to the saturated vapor part, but still in the mixed region. Mixed region means that we have a lot of vapor and a small amount of liquid. This small amount of liquid is usually in the form of droplets. Then this so-called wet vapor has to be cooled down. I mean, the heat has to be removed. It will be done by the so-called condenser, which is also a heat exchanger using some cold source. And then we will go back to the first step and we can start it again. The problem is that we are producing some gross power, but some part of the gross power has to be used by the pump. Approximately it's 15% in an average small Rankine cycle device. And also if we are using air cooling, the air cooling needs big air coolers, and they are also using around 10 to 15% of the total produced electricity. It means that we are going to lose 30% of the produced electricity just by running the device itself. Also, I put this Carnot rectangle. You can see that it's quite nice. So it would be a good device, just it seems to be a little bit too expensive. There is another problem. I said that upon the expansion, we will end up in the wet vapor region. Wet vapor region has a lot of tiny droplets, and the tiny droplets has quite big speed. And if, for example, if you are using a traditional expander, which is a turbine, then the turbine blades will be damaged by these droplets. Therefore, it's not so good to use this kind of expansion. What can we do? We can simply superheat the whole system. So instead of starting the expansion in the saturated liquid state, we can heat up the system. Pressure is still not so high. Temperature is already quite high. And you need a third heat exchanger, because in this case, you are heating up a vapor, pure vapor. So there will be no phase transition like in the evaporator, and therefore it has to be a different device. So even we made this total system is a little bit more expensive. And then if you compare this superheated Rankine cycle with the big rectangle, because now we have to draw the rectangles always the maximal and minimal temperature, you can see that the efficiency compared to the potentially best Carnot efficiency is even smaller. So we are on the wrong size. And also we have to make an inventory. We have 4 heat exchangers, 1 pump, 1 expander, 1 generator, and a lot of pipes. We have to remember for this one, because in energy engineering, not the kilowatts or kilowatts hours are the most expensive, but the most important, but the price, unfortunately. So here are the problems. Heat exchangers are expensive. Pumps has self-consumption. Also, there is something which is called boiling crisis. It can happen in the evaporator, that on the cold liquid size, there will be bubble formation on the hot surface of the heat exchanger. and sometimes the bubble will not be able to move away, so they will form a more or less compact vapor film on the surface of the heat exchanger, and then the heat exchange between the cold and hot liquid will deteriorate, and sometimes it can even cause steam explosion because there will be some overheating in one side. Also, as I mentioned, if you have small heat source, then the investment cost and operational cost should be as low as possible. So we have these problems, they have to be solved, and we have to solve it in high pressure supercritical fluids. The reason is that this is a high pressure meeting. So always we have to find a proper solution which fits into the audience. So what can we do with supercritical fluids? There is something called transcritical Rankine cycles. You might remember that in traditional Rankine cycles, we had a short compression line, and then we heat it up, and then upon heating, the liquid state reached the evaporation state. If we are using bigger compression, then we can go above the supercritical pressure, and then by heating the high pressure liquid like fluid, when the pressure is higher than the critical pressure, you might have heating without boiling. So here it will be some liquid-like, it will be some vapor-like, but technically there will be no boiling, no bubbles. So you solved a lot of problem, because in this case, you have to use only one heat exchanger. Well, it has to be more sophisticated than the previous one, but it's still only one instead of three. And you also solved the boiling crisis. Of course, there might be some other problem. From transcritical Rankine cycles, industry are using more or less only 3 different fluids. Water is used in traditional fossil fuel supercritical power plants. There are several all around the world. Also, there are some plans to build similar nuclear power plants. It is called a 4th generation supercritical water reactor. It will run between 23 and 25 megapascal. And also carbon dioxide and propane are very popular when we have to utilize low temperature heat sources like geothermal or petrothermal, which means the same like a geothermal, only it's from oil or gas, or some low temperature industrial waste heat. The reason is that the critical temperature of carbon dioxide and propane is very handy, especially if we are using geothermal water for heating. The problem is the new problem that we will have the so-called Vidom anomalies close to the critical point when we are heating up the system on a supercritical pressure. What does it mean that we have heat Vidom anomalies? It means that in supercritical fluids close to the critical point, some of the transport properties might be extremely high. And when you have the combination of this extremely high or extremely low quantities, this is, for example, the constant pressure heat capacity, then there can be 2 different problems, the so-called deteriorated or enhanced heat transfer. In one case, you cannot remove all the heat what you want, and in the other case, you will remove too much heat. The deteriorated is the bigger problem, because if you cannot reach your the heat what you want to remove, for example, in a supercritical nuclear power plant, then it might be a huge accident. And therefore, in supercritical power plants, you have to know exactly the thermal properties. And I said that the supercritical nuclear power plants will run on 23 or 25 megapascal, but this pressure will be reached by a pump. And when you are using the pump, the pressure is not exactly 23, there will be always some fluctuation around the pressure. This fluctuation can be even 0.1 bar, so 0.01 megapascal. And it means that because in the Vidom region, these transfer thermal properties are very expensive to the actual pressure, you can have even 2 or 3% differences between them. And it might mean that you just calculated that everything will be okay, but no, because the CP is a little bit higher and you will have deteriorated heat transfer. So it will be very difficult to make very exact calculation for supercritical power plant, but we have to solve it somehow. Inventory, again, we still need for both system, the traditional Rankine or the transcritical Rankine, we need one pump, one expander, one generator. Concerning the pipes, the transcritical Rankine cycle, it is called transcritical because the cooling part is subcritical, the heating part is supercritical. The pipes should be much bulkier because we have higher pressure, and we need only 2 heat exchanger, one for heat addition and the other one for the heat removal. So therefore, we solved one problem associated with heat exchange. We solved the boiling crisis problem. Also, at least partly, we solved this investment problem, but we have a new problem with Vidom anomalies. What can be done? In geothermal power plant, there is a very nice and tricky version. How can you solve the problem associated with the pump? They are saying that, okay, let's put the first heat exchanger, what is making evaporation, below the earth. But what I mean, not only 10 meters, but 500 meters, 600 meters. So to the geothermal environment, or even to 1 kilometer. The heating will be done here, and the pressure will be high, not because any pump are used, but simply the working fluid, which is condensed on the surface by air cooling, it will turn back to liquid, and the barostatic pressure of the liquid will make the pressure of this system. Of course, it's very difficult to make a big power plant like this one. There are some smaller pilot existing, but there are 2 problems. The first problem, that if you want to utilize most of the work which is coming out from the expander, you have to put the turbine very close and also the generator very close. It means that the turbine and generator and evaporator has to be in underground, 1 kilometer depth. It's an expensive way. Alternatively, you can put the turbine and the generator to the surface, but in that way, you will have a huge pressure drop between the evaporator and the surface, and also temperature drop, and then the efficiency will be much lower. That is another solution, and this is really nice. In some oil field, people realize that they are using carbon dioxide, pushing down to the underground just to increase the oil well flow. And the carbon dioxide is going down, then it will be heated up, and in some oil well or gas well, it will come up in gas form, and it can be condensed and then put back to the underground part, and then it will make a cycle. It can be helped with a small pump, but technically you do not even need the pump, and you do not need the heat exchanger, because the heat exchanger will be the geological location. The only problem that to find a good location where this thermodynamics per pit to mobile cycle can work, it's very difficult. As I know presently, there are less than 10 locations known around the world, and one of them is in Hungary, in Zala County, and they already had 1 month long cycle, and it was constantly, the carbon dioxide was constantly running around and around, and it generated something 200, 300 kilowatt, which is not a nuclear power plant, but it's a quite nice number. So here we also have carbon dioxide supercritical, which is a high pressure, but not extremely high pressure. So in this way, the pump problem can be solved, but the investment cost will be extremely high. So this is not the best solution. Therefore, coming the last part, what can we do to have a very simple thermodynamic cycle, a bare-bone thermodynamic cycle, which can turn heat to work? First, we have to investigate what are the necessary steps for the power cycle. Of course, because we are converting heat to power, therefore we need a heat exchanger for heating, and we need an expander to turning part of the heat to work. We also need the second heat exchanger because only part of the heat will be turned to work, and therefore the leftover has to be removed. But actually, we do not need the pump. Technically, we need the high pressure because the high pressure is needed to drive the turbine somehow. But why do we need a pump? Can we make high pressure without pump? Of course, we can make it, and let's see how. Let's have a temperature entropy diagram just for gas. We have an initial state of the fluid. It's a low temperature, low enthalpy gas, and we can heat it up in two different ways. We can do it in isobaric or isochoric way. Isobaric and isochoric heating is very different. Let's say we are using isochoric heating, and when we are reaching the maximal temperature provided by, for example, the geothermal well, then simply we can make an expansion. And in this way, we have a so-called trilateral cycle, an isochoric heating, and adiabatic expansion, and then isobaric cooling. This is the so-called Lenoir cycle. Lenoir cycle is not very good. If you compare it with this Carnot rectangle, you can see that it's really, really bad. And sometimes Lenoir cycle is still used with internal combustion engines, but only for cheaper devices like lawn mowers. What can we do? How can we make the Lenoir cycle better? For example, the first step that we have to run it with external heating because we have to utilize geothermal heat. And then we also have to make better efficiency. Better efficiency can be done if we will make one of the heating isothermal. And it means that we have to do a transcritical cycle. This is carbon dioxide. First, let's see the black one. We have a isochoric heating, adiabatic expansion, then an isobaric and isothermal cooling. We had a nice triangular cycle. If you compare it with a rectangle, you can see that it's almost half, so it's not bad. The problem is that if you are using these numbers, the highest pressure of the system will be 277 megapascal. For your community, it's not big. For an energy engineer, it's an extremely big, because even the very high pressure power plants has maximum some 20 something megapascal. So it's 10 times higher what can be reached in industry. And even if you make smaller triangle, it's still 100 megapascal, so it's still not so high. There are some problem. First problem that in the market we have a lot of isobaric heat exchanger, but we have only a very few isochoric. It means that the prices of isochoric heat exchangers are quite big. And as you see here, upper and lower temperature pairs are always connected. So if you have one lower temperature, which means, for example, air temperature, then you can utilize only one high temperature source. If you have another high temperature source, then it will need a different cycle. Pressures are high. As you said, it's a very, very big problem. And even if you go down, still we have high pressure. Here I have a lot of different triangles, and the smallest one inside, it is a triangle between 303 and 373 Kelvin. It is very good for a geothermal, low temperature geothermal well with air cooling, and the pressure is 25 megapascals, so it's on the limit of our potentials. But as you can see, because this triangle is quite small, therefore the power will be also quite small. We can compare the maximum and minimum temperature pairs. Then most of the so if you have a geothermal well and you know that the geothermal well temperature is 350, then you have to find a cooling material which can cool it down to 303 centigrade. And you have to do it on potentially in low pressure. But how can we make the pressure lower? And in this case, the second law helps us, because the second law is talking about entropy and all the bad thing of the world. And also it means that there is no such kind of thing like ideal isochoric or ideal adiabatic processes. So if I have something which is not ideal isochoric, but more or less isochoric, then instead of the solid line, we have something like a dotted line. So I will go up on a different quasi-isochoric way, and the temperature and pressure at the end will be different. Also, then I will have a non-perfectly adiabatic expansion. It means that the slope will be not infinite, but some finite negative. And it means that instead of the solid rectangle, I will have these dotted or dotted dashed rectangles. It means that if I choose properly my quasi-isochoric heating device or my expander, then I can choose the location of this upper point. This can be here or even here. So I can utilize more and more temperature, more and more heat sources. And then at the end, very end, I hope I still have a few minutes, I just compared the traditional transcritical Rankine cycle, which is also not bad, but it has, as I said, high self-consumption and need a lot of extra devices. With the Lenoir cycle, which do not have self-consumption, no need for pump, but has lower efficiency, lower gross power, and also need an isochoric heater. So every time when you have a heat source, you have to compare the gross power produced by the potential transcritical Rankine and the transcritical Lenoir cycle, and depending on the gross power and the self-consumption, you can decide whether the Rankine or Lenoir cycle would be the best. There are occasions when this one is good, in other occasions the other one, but in several times you have to make very, very, very detailed financial calculation which one would be the best. And with this Lenoir problem, well, we solved almost everything. Heat exchanger is a little bit still too expensive because we need special one. And of course, we have to handle the Vidom anomalies somehow. But it still does mean that the Lenoir cycle with externally heating and with transcritical cycle can be a good solution for geothermal and industrial waste heat sources. We can make a few hundred kilowatts, not a few thousand megawatts, but that few hundred kilowatts can be used on spot, and therefore there would be no even transport cost for the electricity. So it can be a good solution for a sustainable future. Thank you for your attention.
Thank you very much, Attila. It was really exciting. It's great that we are having presentations from different fields and from energy engineering. I'm not sure if it's really something we are all familiar with. We have one question so far, if you allow me to read it. Do you think that thermal energy can reach up to significant amounts to contribute to the elimination of fossil fuels? Can you compare geothermal with solar, wind, and water in terms of future alternatives to fossils?
I know only the Hungarian numbers. In Hungary, if we would utilize all the Hungary has quite good geothermal potentials, but we have only low temperature geothermal sources, which means that 120 centigrade maximum. In Indonesia, they have even 200 centigrade, which is a different story. But in Hungary, we could generate something around 1 megawatt electricity. 1 megawatt electricity is roughly 20% of the need of this country in present day. Because, of course, if we will have an electric car or hydrogen-driven car, it will be increased. But this 20% is more or less base load. So it means that it's coming constantly. It doesn't need extra batteries to store them like for solar power. So it can contribute. I think everything which is bigger than 1% has a significant contribution. So, and this 20% is quite big.
Okay, thank you. I also feel that it's important that you mentioned, and I fully agree, that we have different possibilities and they are not competing, but just each has the part in the energy portfolio. Am I right that this is what your opinion is? Yeah, sure.
Yes.
We have a second question. So can you please elaborate on the environmental effects of geothermal energy?
Well, it's very strange because they're always saying that geothermal is the best and no carbon dioxide emission and nothing, but practically everything which is coming out from underground, it has carbon dioxide and even natural gas. So, and in most of the geothermal power plant, they are even using this natural gas which is coming out with the thermal water. They are using them on gas engines. But there is another solution, so-called dry geothermal wells, when no fluids will be removed. Simply you are using the hot rock. So you have a 2-kilometer long shaft, and you will put a heat exchanger down, and you will use your own fluid, which can be even supercritical carbon dioxide, because it has quite good thermal properties, just to remove the heat. And I think this dry well solution would be the really good for the nature, because there would be no pollution. Presently, we have a lot of pollution. In a lot of geothermal installation, they are just letting the cold geothermal water to some river, and it's not very good, because that's very different water chemically. They have a lot of salt inside, and it's not good for the living waters.
Yes, this dry well solution is exciting. We have another question that do you think that the geothermal can be alternative in other geographies in the world? Because 20% in Hungary is quite impressive.
In China, in Indonesia will be the biggest producer of geothermal electricity in the next 1 or 2 years. Presently, the United States are also huge. I mean, they can produce several 1,000 megawatts, but Indonesia is a volcanic region. So in Hungary, Iceland, Greece, Italy, and part of Turkey, very good, because they have a lot of high temperature parts. Well, for Scandinavian countries, for Great Britain, I think it's not a good solution. But in energy engineering, there is no general solution. Each country. Well, Great Britain has the wind, offshore winds. Hungary has the geothermal, so we have to use what we have.
Okay, thank you very much. It was really exciting. we ran out of the questions, so we are moving to our next presentation. And actually what Attila mentioned is geothermal perpetuum mobile, which is related to CCS, is also leading us to our next presentation, which is going to be given by Lars from Norway about carbon capture and storage. Lars, the floor is yours, or the screen is yours if you are sharing it.
Thank you, Edith, and thank you for being able to show this presentation. And then I hope that you can now see my presentation.
But not in presentation mode yet.
You have not seen the presentation yet?
No, we see the editing mode of your presentation again.
Then I just close it down. And then I
ask a little bit of patience of the audience. So when we tried sharing the slides, we had several problems with sharing the presentation mode. So we're just trying it again. Now it shares your presentation mode. So we are seeing also the next slide.
Yes. So again, thank you for...
So it's still not the perfect one, because we see two slides at the same time.
So when do I get rid? Do you
display
also
settings maybe?
Okay, then I try even one more time.
Now it's great. Perfect.
Now you see one slide at a time.
Yes.
The presentation is about CCS projects in the North Sea, from high pressure to low pressure. The topic should be about high pressure applications and CCS in general is in many different applications. But on the front slide, we have our pocket version of a carbon capture plant. This carbon capture plant is in our university in Porsgrunn, that is close to Oslo. And we have an absorption column to the left and a stripping column to the right. The absorption is at atmospheric pressure, and the stripping is performed at 2 to 3 bars and using steam, low pressure steam, to heat the stripping process. And the absorption can be from 1 atmosphere to up to 100 atmospheres. First, a little about CO2 capture and storage technology, and then just a little about the need for CCS. I tried to go a little through the history of early high pressure applications, and that is carbon capture from natural gas. And this is by nature cheaper due to no pressurization and also to slim columns. And then I will turn to today's atmospheric applications. And we have a large project going on with storage under the North Sea. These atmospheric applications, they are expensing due to several things, but typically very large and expensive columns and much heat needed. And then I will end with a little about the future of CCS. This is a little about the technology, and I will only going through CCS by absorption in amine solvents. And again, this process can be performed at a high or a low pressure in the absorber. I guess that most of you have seen the outline of this process before, and from a chemical engineering point of view, it's is perhaps one of the most common processes with absorption followed by desorption or stripping. So the CO2-rich gas is coming from the left into the absorber. Then an amine solution absorbs the CO2. The rich solution goes to the stripper where heat is added, and in this reboiler there is in many cases lots of energy used to strip off the CO2. And on the top of the stripper to the right, then we have a compressor, and this CO2 can go to a pipeline, or in some cases the CO2 is directly to an underground or an undersea storage. Then the need for CO2 capture. About the climate, I will only state that the CO2 concentration in the atmosphere increases and the temperature increases. And we are soon approaching 1.5 degrees heating, and then we have a political international agreement of an aim to limit the heating to 2 degrees. And this is an old curve. If you are following these strategies, there have been made lots of these scenarios. And this curve is indicating that if we are doing nothing, we will perhaps reach 6 degrees heating. If we do a lot of things, we can probably reach 2 degrees heating within 2050. And now, if we are going to do that, we have to do several things. And it is indicated here that CCS will stand for 14% of the remedy. And if we look at the timeline, we are now in 2024, and now we have to start with large-scale CCS applications to reach the 2 degrees level limitation. And I'm afraid that we are late, but from the process engineer side, we definitely have a challenge here, and we want to take the challenge. And I think that CCS will have an important part in the limitations of the temperature increase. And to go back in history, locally here, I am, as I say, located in Porsgrunn. And in Porsgrunn, we state that we have had the CO2 capture since the 60s. We have an ammonia plant on the picture where we have close to 1 million CO2 tons of CO2 every year. And what is done is that a fraction of this is absorbed from synthesis gas in water under pressure in the 4 absorbers in the middle, and this has happened since the 60s. And in the 60s, this CO2 was exported, and some is sold as CO2, and that is most for beer and mineral water. And there has been a long-lasting export on ship. And more of this CO2 could be captured if it could be stored. Then we go out to the North Sea, and this is about CO2 capture at the Sleipner field. The process of processing the natural gas is performed at about 60 bar on the top of the platform. This is below the reservoir pressure and above the pipeline pressure. And this process has been performed since 1996. And the reason why they removed this CO2 was due to 2 things. The one thing was to reduce the unnecessary transport of CO2 to the European continent, and partly to reduce the CO2 tax. And in this project, CO2 is stored actually about 25 million tons until now in formation with salt water and aquifer. And that is a layer between the ocean bottom and the Sleipner oil and gas field. This is a picture showing the principle of this. We have the Sleipner gas field on the bottom of the picture. Then the natural gas is processed on the platform. Then the CO2 is taken out from the natural gas and injected in a salt water layer. And here there are already 25 million tons. And the tests show that the CO2 is actually staying in this salt layer formation. And we on the picture where we have Norway and Scotland on the other side, we have a large formation where we have possible places to store the CO2. In Norway, similar things is done at the Melkøya LNG plant that is near Hammerfest in northern Norway. And I think I have taken this picture, and I think it's fascinating that the size of Hammerfest city center that is closest to us, that is the smallest thing, and then the coastline is bigger than the city center, and behind in the picture we have the LNG plant, which is much larger than the town of Hammerfest. And at that LNG plant, there is an absorption plant for CO2, where CO2 is removed under pressure, and then the CO2 is sent back and stored in an aquifer or a salt water layer under this snow white gas field where the gas comes from. And this has been in operation since 2008. Then we turn to atmospheric pressure. It is in a way more difficult or more costly to capture CO2 from atmospheric exhaust. One of the first places they did that at large scales was in Saskatchewan in Canada. The place is called Boundary Dam. And this was the first large-scale example of CO2 capture from a coal-based power plant. And Cansolv was the technology. And this could be done because the CO2 is used for enhanced oil recovery, EOR, and that means that they could get some return on the money spent for an EOR utilization of the CO2. And we have the coal power plant to the left, and we have the CO2 capture facility to the right, and then we have a feeling of how large these columns, the CO2 capture columns, has to be. Now we return to Norway, and this is also in Porsgrunn, where our university is located. Here we have a cement plant within the Heidelberg, and now they are building the CO2 capture plant with absorption at 1 atmosphere, and the plan is to have ship transport to the Norwegian west coast and then storage under the North Sea. And then we have other CO2 emitters close to us. This is a waste combustion plant at Klemetsrud in Oslo, and there is a plan to capture the CO2 from here and bring it to the west coast. And there is also CO2 capture in a large test center, Mongstad. This test site is close to Bergen, and it is close to where the storage of the CO2 in the North Sea has its land-based facility. And at this test center, with this large absorption column that is 60 meters high, and here they have tested processes for Aker Solutions and Cansolv. They are two of the commercial processes for CO2 capture at atmospheric pressure, and also other processes like the Alstom chilled ammonia process is tested here. This is a picture of this general project, which is called the Northern Lights, and the plan is to start this in the beginning of next year. So we hope that everything works fine. And on the map, it is seen that Oslo and we are about here. The ship will transport the CO2 to the west coast, and then the CO2 is transported in a pipeline to a location under the North Sea. And then I go for the conclusions. And that is a sort of discussion about carbon capture and storage cost. And the cost of CCS is in the order of magnitude 50 to 200 euro per ton CO2. This depends on several factors. Then the start of this was based on CO2 separated from synthesis gas, natural gas at high pressure. And this is employed because it is economical compared to CO2 tax. This was a reasonably cheap solution to start with. The CO2 capture cost at atmospheric pressure is now around 100 euro per ton. And it is still higher than the quota price for CO2, but with some help, in this case from the Norwegian state, it is possible to run projects like this. And for the future, it is expected that the capture cost and the quota price will become closer. And the development of technology within CCS will reduce cost. And the storing capacity under the North Sea is now developed. And there are quite a lot of contracts set now where companies on the European continent, they make plans to transport CO2 to be stored under the North Sea. So that was my presentation. Thank you.
Thank you very much. It was really great to see all these industrial large-scale applications and plans you shared, and also this last slide about economics. I think it's really something special, so we don't really see it that much. Our first question arrived, and I ask everyone in the audience to share their questions in the question and answers button under there, because then we can see it and answer it. So the first one is that, is capturing existing CO2 already in the atmosphere an issue under discussion?
I will say yes, because what we call direct air capture, that is definitely a hot research activity. However, and we can divide CO2 capture from the atmosphere into two. The first is the natural one. We could, for instance, feed more trees and making available areas for plants and typically a forest to absorb more CO2, and then that is a sort of capture. What you probably ask about is industrial direct air capture, where we make an industrial facility where we have large amounts of adsorbents. That is what is normally suggested, and then we have some desorption also of the CO2 and collection. So this works in many ways like normal industrial CCS. However, so far this direct CO2 capture from the atmosphere at industrial scale is much more space consuming and much more energy consuming than CO2 capture from exhaust gas.
Do you have by chance any comparison with planting trees and industrial capture of CO2 from atmosphere? I mean, that's either environmental aspect or economical aspects regarding comparing these two possibilities, because for me it would be so logical to go for the natural way and plant trees.
Yes, I'm not sure if that was the question or...
Yeah, the question was whether you have any data in comparing the industrial capture of CO2 from air with forestation. So if we want to compare it from an environmental point of view or economical point of view, then whether you have any data on that.
Okay, I think that there is not any full scale. There are many pilot scale activities on CO2 capture from the atmosphere. However, to my knowledge, there are not any large scale facilities, and because of that, so far we do not have any real examples where we can make comparisons with traditional CO2 capture and in a way we do not have any examples where we can actually compare with a forest. But the idea of using forests for capturing and storing CO2, that is done by nature, and forests can also be made more industrial, but the direct air capture examples, I do not know of any that has come so far that we have any data to compare with.
Thank you very much for the detailed answer. And I think I would like to thank you the presentation and the talk. It was really exciting. And maybe at the end of the session, we can come back to discuss some further things. But now it's time to pass the word to Maria Dolores Bermejo from Valladolid University. And she's going to talk about that, what to do with the CO2 if we don't want to store it, how we can use it for other purposes. So the floor is yours. Please share your screen.
Thank you, Erik. I'm going to thank first to be invited to this interesting colloquio, to chat. And I'm going to talk about the processes for transforming CO2 in something, in concrete to formic acid. It has been mentioned that with the Paris Agreement, the objective was to avoid to increase the temperature of the air more than 2 degrees C. For doing that, several actions are taken, and one of the main one is stop using fossil fuels. But as they still will be needed for a few years, it has been decided that Professor Oy explained us to use capture of the CO2 and storage. But if together with storage we can use this carbon dioxide, we can decrease the cost of capturing and have raw matter for fuels, chemicals, or materials. And what happened in the future? In the future, ideally, the fossil fuels will not be used, but still there will be CO2 sources. For example, in the biogas is containing CO2, other biological processes are producing CO2, and also burning the biomass is producing CO2 that can still be captured and use this CO2 as a raw matter. Our proposal was the hydrothermal reduction of CO2. CO2 in this process will be converted in the shape of bicarbonate in water environment at high pressure and temperature. These processes are inspired in the processes that are happening naturally in the deep ocean near the submarine volcano, and these processes are in the origin of life. In this process, the main product obtained is formic acid, but with the appropriate reaction time and catalyst, other products such as methanol or methane could be obtained. And as reductant, they can be used metals, hydrogen, or biomass. Important advantages of this process is that just capture the CO2 by absorption with sodium hydroxide, with amines, or even with ammonia. This CO2 dissolved in basic solution can be directly taken to the hydrothermal reactor without separating or purifying the CO2, and then we have, after the reaction, directly the product. So we don't need an intermediate purification or compression. This could be a conventional carbon capture process from amines. We have an absorber, a desorber, and then we have to recover the amine employing high pressure or high temperature steam, and have a compression step to send the CO2 to storage. In integrating this absorption process with hydrothermal reaction, we substitute these equipments that are the most energy consuming equipments with hydrothermal reaction, and energy could be integrated as in the other place, but we have directly products that can be liquid and that can be easily used or transported. The objective of our research this last year has been to study the different processes of reduction of CO2 capture in basic media in order to achieve its scale up. We can have the CO2 as carbamate or bicarbonate in ethanolamines, bicarbonate, or using ammonia as capture ammonia solution as capture solvent, and the reductant could be biomass, metals, or hydrogen. First, I will explain our results using biomass. When we began our research, there were previous results in which CO2 was reducted in aqueous medium at high pressure and temperature at 300 degrees, more or less, using a reductant glycerin or isopropyl alcohol. In the literature, it was explained that these alcohol groups were the responsible of the reduction. So we thought lignocellulosic biomass can be transformed in high temperature water in hydrothermal media, and after the decomposition of these products, we have hemicellulose that is dissolved around 150-130, cellulose that is dissolved at temperature higher than 250, and lignin that is partially dissolved. It has aromatic groups. But these two fractions have a lot of alcoholic groups. So this substance, sugars, alcohols, polyalcohols, aldehyde with alcohol groups, are in theory are susceptible of produce the reduction of CO2. So for testing, what we did was to make extensive experiments with a lot of substance that could potentially be derived from CO2, making experiments at 300 degrees and 150 minutes in batch reactors. Very simple experiment, but a lot of them. And we test a lot of substance, and almost all of them, except for acetone and for phenol, they were able to give formic acid from the bicarbonate. The one with higher yield was glucose. So we deep into these results and we make further experiments with glucose that normally is used as a model compound of biomass, lignocellulosic biomass. So we make experiments. We know that the formic acid could come from bicarbonate, but also from biomass. So we made experiments using bicarbonate with asserted carbon in order to detect the origin of this formic acid. After the experiment, we saw in the black dots, we can see the total formic acid, and in the white dots, the formic acid coming from bicarbonate, from market bicarbonate. We can see that with reaction time in batch, this amount is increasing. This means that this reaction of reducing CO2 is slower than the reaction that forming formic acid from the biomass, and that at the end, more or less half of the formic acid is coming from the biomass and half is coming from the bicarbonate. This is good because with reaction with biomass, it is normal that it appears a lot of different products. So in this way, we are improving as well the selectivity of the other part of the reductant, that is oxidides. We check that this amount of CO2 coming, of formic acid coming from the CO2, from the bicarbonate, was increasing with temperature. The maximum is at 300 degrees because at higher temperatures the formic acid begins to decompose. And also we test several catalysts, and we observe that some of them were improving the total amount of formic acid, and some of them were improving, that are the dots, the proportion of formic acid coming from CO2. So we can have catalysts that influence in one or other of the two simultaneous processes that are happening. So we scale up the process for glucose in a pilot plant with 2 kilograms per hour of solution. We have a depressurization valve, so we can work with very short residence times. And we found that from very low residence time, even of seconds, we can have high yields of formic acid, and that from the beginning, from 10 minutes, that was the first experiment that we made, using market bicarbonate, we could have important yields of formic acid coming from CO2. This is explained by the best operational condition at continuous, where the heating is faster, because at low temperatures, the formic coming from biomass is favored. So we have promising results. Our next step was testing real biomass. So we test a lot of biomass first in batch with catalysts. The most successful catalyst was palladium over carbon, again, over activated carbon. And we found that using this catalyst, even at low temperature, we can have important proportion of formic acid from the bicarbonate, but the total amounts of formic acid were higher at higher temperature, 300 degrees. And the most successful biomass were those with higher contents of cellulose, the pure cellulose, and then the wood and the sugarcane bagasse. So we obtained the Naturgy Award, and with this we were able to scale up the process. First, we made testing with the small continuous process. The process was the same. We heat water and we pass through a vessel full of biomass, through a biomass bed, and we obtain it making experiments at different temperatures that we have at temperatures around 150 important amounts of acetic acid, and that at higher temperatures we have peaks of lactic acid and formic acid. So we decided to implement the operation for the bigger pilot plant with a step of operation at 150 and a second step of operation at 300. We test this way of operation with several biomass, different biomass, coffee waste, cocoa shell, wood, core leaves, pistachio shell, all of them lignocellulosic biomass was very different. And we observe in most of them the same behavior. First, a peak of acetic acid, and then a second peak at 300 degrees of formic and lactic acid. So now we are in the process of scaling up the plant. We have a 1 liter reactor. The plant is intended to work between 5 and 25 liters per hour and transforming amounts of CO2 of between 100 and 500 grams per hour. Okay, this is ready. We can have the pumps, the vessel, the catalytic reactor, and the plant is going to work in 2 steps. A first step in time where it's working at 150, and a second step when it is working at 300, and the effluent is going to pass through a catalytic reactor to transform the unreacted products to formic acid. Now I'm going to talk about the second process, using metals of hydrogen. Previous results in literature with bicarbonate show that if we react this bicarbonate in aqueous solution at temperatures of 275, 300 degrees with these metals, aluminum, zinc, iron, or manganese, this metal release hydrogen, and in situ there was produced the reduction of CO2 to formic acid. This was a very rapid and selective process because the slightly basic medium was able to stabilize the formic acid, and we can have yields of 70% with respect to the bicarbonate in the first minutes of reactor. So we thought that this process is very nice. We have the problem that we have a waste of the oxidized metal that of course could be recovered by reduction. And we have also the issue of the high temperature of 300 degrees. So we thought if we capture this CO2 with amines of ammonia, we can have our aqueous solution more concentrated, and also this kind of bicarbonates of amines or ammonia are more reactive than the sodium bicarbonate. We test in batch, and we found that if we could make the reaction with ammonium carbamate, that it has an equilibrium with ammonium carbonate. It would be the product of capturing CO2 with ammonia in aqueous solution. And we have yields at 120. This means that we have reduced a lot the temperature to around 10, 20%, 25%. And we realized that the pressure was very small. This means that the hydrogen was not releasing from the metal using this solution of ammonia or of ammonium carbamate. If instead of using the metals, we inject directly hydrogen gas, we of course have higher pressure, and we have formic yields, acid yields very high. The formic acid yield was directly dependent of pressure, of the amount of hydrogen. So we study the release of hydrogen from different metals using different basic solutions, both of the original capturing solution of ammonia, of sodium hydroxide, or of amine, or of the amount after capturing the CO2. It means of the bicarbonate or of ammonium carbamate. And we see that this solution of ammonium carbamate of amine, they were giving yields of releasing of hydrogen of 3%, more or less 3%, 3%, while this solution of the direct sodium bicarbonate or sodium hydroxide, they were giving yields in much less time of 70%, 80% of releasing hydrogen. So we know that we cannot make this process with metals. We have to use gaseous hydrogen. But this can be an advantage because it's easier to manage that the metals, we don't have a metallic oxide after the process, and also it is expected that in the future we will have enormous availability of green hydrogen, sorry. So we test the reduction of CO2 capture with two amines, AMP and AP, at different pressure, 20, 30, and 75 bars, and a different reaction time at three temperatures, 70, 100, and 125. And we obtain high yields of transformation of this captured carbon into formic acid, even at 70 degrees. So this was a very interesting process because we have high yields at a relatively low temperature and with hydrogen, gaseous hydrogen that can be easily to implement. So we continue our experiments. We test a lot of amines. This was the originally tested amines, and we see that we are having good results with EP, the AMP, the monoethanolamine that is very used in industry, the tris-fluorohydroxyethyl aminometano, and also with some secondary amines. The best results were with the isopropylamine. And with many of the amines, the best results were not found at 120 degrees, but at 70 degrees. So we have a very good results of very good conversion of formic acid at 70 degrees and moderate pressure of 75 degrees, 75 bars, sorry. So still these results can be optimized. These are only preliminary studies. And with these results, we also check that the amines could be most of them recovered. So we make analysis of NMR of the initial solution and of the final solution, and we could see that the amine was recovered. So the process was very promising, and we had a funding from the Spanish government to make a pilot facility of 1 liter per hour of aqueous solution. We are thinking in working with 30% in weight of amine, and this could be 90 grams of CO2 per hour. The amines will be absorbed at atmospheric pressure, and then the water solution will be compressed and reduced with hydrogen. We have availability of an electrolyzer. We still don't have solar plates, but it could be working with electricity from solar plates. And then after the reaction, we will have the formic acid. We will implement a system for recovering for recirculating the amine by membranes or by distillation. This is in process. We have a photo of the current state of the facility, and we still have 3 years more to develop this project. And as conclusion, that the integration of CO2 capture in basic solution and reduction of CO2 media can be a powerful combination to mitigate the CO2 problems. That is possible the simultaneous conversion of biomass and CO2 in hydrothermal media and in semi-batch, and that combining temperatures and extraction times, we can have some fractionation of the products. That is the process of reduction CO2 with metals. When the CO2 is as bicarbonate, it's promising, but when we are using solution of amines or ammonia, it is hindered the release of CO2, and we have to use green hydrogen. But with this green hydrogen, we could produce formic acid in high yields at moderate pressure and temperatures. And we have a complete recoverability of the amines. Thank you for your attentions, and I'm at your service.
Thank you very much for this exciting talk. A lot of research results, and I'm not sure I understood everything. So I hope that there are a lot of questions, so you can clarify a lot of details. And yes, we do have. It starts with, this may not be a proper question for this talk, but I still ask it with apologies. Do you think that conversion of CO2 to precursors of basic chemicals for chemical industry can be more efficient if conversion is made to take place by microbes or enzymatic processes?
I really don't know about enzymatic process. They are making at lower pressure. They are making at lower temperature. But of course they are alive things, and they are more delicate in some sense. So for the moment, I cannot compare, but I think that at least in a small scale can be very interesting. But it is as far as I know, most of the process of transforming CO2 that are at TRL 9 or something are real chemical process working at high pressure, high temperature. So I think that even this more biological process are interesting. I think that maybe the future can be in industrial process like this for some applications.
Thank you. We have a question saying that low temperature, low pressure operations with a question mark. I'm not exactly sure what the question was. I don't know if you have any idea. Maybe just referring to the enzymatic one, that could be a benefit of biochemical conversion, that it's lower pressure and lower temperature. I don't know if there are any further questions. I don't see so far. Yes. The answer was there that it meant the enzymatic reactions. So the lower pressure and lower temperature. Do you think that, and I'm always excited to see that you are not just doing research in the lab, but directly going for scale up and pilot scales and demonstration plants. And this is really exceptional and amazing. Do you think that the scaling up to real industrial skills is nearby? So that do these pilot skills make it possible?
I hope so. I hope, still we have to solve a lot of problems. This process has to be optimized. But in this moment, there is a lot of interest in this kind of process, and I think that these processes are interesting, and that once that we have the pilot facilities working and we are solving the process, it will be attractive for scale up for companies or for administrations.
It would be really great. So it's so amazing research. And that's really, really amazing. We have another question that has the solubility of hydrogen, carbon dioxide, and adsorbent been studied? If so, what changes in viscosity can be found in the mix?
For the moment, we have made experiments in batch. So for us, we have not issues with the viscosity. So we will have to see when we work in continuous and with the pumping and whatever, if we can find issues. But in principle, we don't expect this that this could be big issues.
Thank you. Someone congratulates to you for a comprehensive chemical engineering project. I just share it with you. I think we arrived to the end of the questions regarding this presentation, and I'm inviting all the speakers to just speak up if they have any comments, questions, discussions among ourselves before we are stepping to the closing part of this session. Do you have any? No. Then actually, I think that we are just arrived to the end of the session, and before telling my closing remarks, I'm sharing you the comments of Professor Maria José Cossero, who is the chair of this working party, that he says that many thanks to all the speakers for their excellent presentations, the interest to motivate our young chemical engineers and researchers in the issues of transition towards a more sustainable society. Congratulations to the EFCE for this initiative and the success with which it is being consolidated. And I fully agree that this session was really exciting. I believe that it was really exciting, a combination of various activities, and also with people from various communities and backgrounds. Professor Imre, as he told us, is a physicist working in energy engineering. And we learned from him that supercritical water, CO2, and propane are all important tools in transcritical energy cycles, and how the importance of the knowledge of thermal properties and thermodynamic fundamentals ensure safe design. This is very important from my point of view, because we are in the supercritical community. I'm not sure we think that much about energy cycles, and it was really something eye-opening for me. Professor Oil, I know him from the Working Party of Education originally, and we also never met in the supercritical community and related events, but it's clear that the carbon capture and storage developments also belong in high-pressure technologies and supercritical CO2. He showed us various examples of large-scale CCS projects, classifying them high pressure and low pressure, depending on the CO2 absorption. Maybe it was to note, because for me it's quite important that when the CO2 is underground, so in the geothermal conditions, then it's typically supercritical anyway. So not just the absorption part could be high pressure, but the storage itself is always high pressure and also elevated temperature. So it's typically supercritical. And Professor Bermejo's work is belongs to one of the large supercritical research labs in Europe, so largest supercritical research labs in Europe, which is located in Valladolid University, Spain. And as I mentioned, these results from going from laboratory to pilot skills is really exciting and unique, I would say. So this viewing the things you are doing. And the combination of CO2 and hydrothermal conditions and catalysis, either with biomass or green hydrogen, leading to CO2 fixation and formic acid formation, that might be an alternative of just storing of the CO2. So this session was a wide scope, because we can save energy and save CO2 emission by optimizing our energy cycles. We can store CO2 underground, which we produced or which is present in the atmosphere, if we can separate it, or we can convert CO2 to valuable materials, and instead of using fossil fuels, we can use the CO2 to support our industry for the raw materials. So this is a wide scope how the high pressure technologies and supercritical CO2 can support the sustainable future. So I hope that you enjoyed it, and I would like to thank first all our speakers for sharing their wisdom, experience, and of course your time, because preparing the presentations and being here is just a lot of work, I know. And we highly appreciate the excellent organization. So thank you, Martin. It was really great and everything worked fine. And last but not least, I would like to thank everyone who is here, all the participants asking the questions and listening to our speakers. And I would like to close this session. Thank you very much.